Okay, let's look at 29. We have M is 100 grams. Now you got mg, you use 32, but this is in grams, and so you have to be careful about all that. So you've got the right idea. You know, what you probably want to do, just to be careful about units and so forth, is you have the 100 grams, well, that's 0.1 kilograms, and then my gravity, not that g of course, but new g, my gravity is then 9.8 meters per second squared, and so your m times g is 0.98 kilograms per meter squared, or newtons. You know, so the 32, it sort of works, but what happens is your units, when you take that 100 times 32, you have 100 grams times 32 feet per second squared, and so you end up with this sort of strange unit, 3,200 gram feet per second squared. Now, if you kept track of that through the whole thing, I suppose that would be fine, but I think you're just better off going this way. So I think we'll go with M is 0.1 kilograms and G is 9.8 meters per second squared. And so then you can get your K. So that was 2 centimeters. Same sort of thing. You have your, so we'll get rid of that. You have your 0.98 is equal to 2 centimeters, but these are in meters, and so 0.02, pretty ugly 0.02, so 0.02 times K. So now we've got everything in the same units, and so K is equal to 0.98 divided by 0.02. What the heck is that? That's what, 98 divided by 2, and so that's 49. So I think K would be 49 in this case. And so we've got M is 0.1, K is 49, and then B, they say nothing about dampening, so B is 0. And so to get this thing set up, I guess we're going to have, for part B, you have your mx double prime plus kx equals 0, so we have 0.1 x double prime plus 49 x equals 0. Now, and they mention that they pulled it, I think, 4 centimeters out, and so x of 0 is equal to, I think it was an additional 4 centimeters. I don't have it. Well, let's see. I can look pretty fast. Let's see. I'll look, see what we have here. An additional 4 centimeters is what I'm reading, and so I need to go back to your stuff there. Okay, so an additional 4 centimeters. We'll say 0.04, and then V, well, I think they just let it go from there, and so V of 0 is 0. So we have that, and then they say to solve it. And now, on your very first problem, I noticed on the whole, you're doing fine. You have some derivative mistakes, some algebra mistakes. What I suggest on some of that is you solve this with Sage, solve these with Sage as well as doing them by hand and compare answers. That's definitely one way to go. And you asked me about Sage as well, and so we'll look at that here in a second. But I just wanted to get this started. So we have this, and so I would have something like 0.1 r squared plus 49 is equal to 0, and so in this case we're going to get the pure imaginary situation, and we have r squared is equal to minus 490, and I'll let you go from there. But yeah, on these, that's the kind of thing you need to do. Let me look real quick. 30 says, I'm just looking at your page right now. So it says in 30, you have mass as 1 kilogram. Well, that's great. We'll leave it at that. But then in that case, your acceleration due to gravity is equal to 9.8 meters per second squared again. And then it mentions stretching 5 centimeters for your x0. Well, I would make x of 0 0.05 to keep it in meters. And other than that, it looks like maybe that was the same sort of problem. And let's see, so you're 31. Again, now in 31, it looks like they're using feet, and so let's take a look real quick. Yeah, so 30 looks like a spring. Yeah, 30 and 29 are the same, basically the same problem to start with, but then in C, in 30, it says, suppose the spring mass is suspended in fluid, and so this is where we're getting a B, resistance of 0.25 kilograms when the mass body has a velocity of 2 centimeters per second. Modify the initial value problem in B. Okay, so you're going to have to figure out in C with your 0.25 kilograms and at 2 centimeters, so 0.02 meters, and determine what B is. And that, actually, I hadn't really looked at that, re-looked at that again. Let's see, so I think, where do they, let's see, motion mass hanging in the vertical spring. Yeah, so in the direction, I don't think they mentioned B. It's been a while, so I'll have to go back up here and look at this, at the damped oscillator. So I'm looking back up here where they introduce it. Let's see. And yeah, I think for B, you have to look, I mean, to find the constant B, not part B, but to find the constant B, back up to 1.3. Now another thing you can do, and this is, you know, just to kind of help in general, if you think about units, right, so the units of x are in meters, right, because that's the displacement of the spring. You know, so x is meters. Okay, you have that, and then if you look at k, k is our I got to go back up here and look at it. Right, we had newtons, so kilograms meters per second squared over, and we divided by meters. So, so one way to look at it is that K is newtons per meter, like that. And so when you put x times k, you should get newtons, or kilograms meters per second squared. Well, so then that's the same thing. If you have x prime, that's meters per second. And so when you multiply by b, b times x prime needs to be newtons. Okay, well, so if that means b has units of newtons, which is kilograms meters per second squared, times seconds over meters. And so B is kilograms per second, I guess. So, you know, that's one way to help you out, because again, what they told you was 25 kilograms at 0.02 meters per second, I think it was. And so I gotta make sure my units are correct here. Because as I'm looking at this, let's see, so we need newtons, so K, X, yeah, that's newtons, and so newtons are kilograms meters per second squared. Got that. Divided by x prime. Kilograms per second. Yeah. So I'm a little confused on that, because I'm not sure what to do about the meters. And so if we go back, let's see. If we go back here and try to find let's see. Yeah. Let me pause this a second. Still recording. Okay. So, pause. Okay. Sorry for that long pause before I actually paused it. Yeah, the best I can tell, this should be newtons the way the problem is written, and so what you need is your constant B is not well, it is that, but the way I would write it is newtons per meter per second, like that. And so your B in this case is your 0.25 divided by 0.02. Okay, so again, that's 25 divided by 2, or 12.5. And so that's your B, and now you can put everything in there together to work on that. Okay, so on the Sage, you have that first line, T var T, and all that's doing is setting up a symbolic variable. Then you have X, which says we want to call it a function of T. We want f of T, or sorry, X of T. And so that's why they say, okay, we're going to make this a function. So there's X of T. So really they're just saying, oh, I want that function X of T. Now they solve their differential equation. Now the original differential equation, I can read from this and see that it was x double prime plus 3x prime plus 2x equals 0. And so that's what they do, is they're just assigning a variable called dE for differential equation. And they're saying, oh, well, we need the second derivative of x, so we're going to take a derivative of what, x, with respect to what, t, and how many derivatives, 2. And then plus your 3 times 1 derivative, so diff xt, oops, forgot my 1, and then finally plus the 2x, and you need the asterisk in there. And then they use the double equals when they're talking about equality, like equations. They use a single equal when they're talking about assignment. And so, you know, there's the differential equation. Then they solve it. Now, what you're going to need to do in Sage, when you put something like this in, you're going to need to do something like, you know, oh, the solution equals dsolve, so that's using that particular package, dsolve, of the differential equation, and then it asks for, you need to give it the variables that you're using, and you have to do it in a particular order. You need to do independent last, so there's independent. You need to do that last, but that gets to the solution, and then for you to see the solution, this is the best way. Actually, I think if you just put that dsolve into Sage, it'll probably show the solution. But this is guaranteed to show you the solution as long as everything's typed in right, and you get to show the solution. And I believe if you look through Blackboard, you know, I have, well, I guess it would have been from maybe Project 3. I can try to look at that real quick while I'm talking here. If I look at Project 3, so this is getting to be a very long video, but I think I can put it on YouTube and work. So Project 3, I can't look at it very quickly right now. So, but anyway, somewhere in there, under one of the projects, I have a very annotated Sage code, and so that can also help you with all this. So with that, we're hitting 20 minutes, and so we'll say that's enough, and stop.